Rotation is the spinning motion of a body on its axis. So people often confuse the terms rotation and revolution. They'll often say something like, the Earth rotates around the sun. It's not exactly true. The Earth rotates around its axis. The axis is the imaginary point that goes right down the middle of it. So imagine if this was a globe, right? And you know how in the globe there's like a rod that goes right down the middle and it spins around that rod. It's the same idea here, except that we don't see the axis, but it is there, and that's the point on which around it rotates. So it does revolve around the sun, but it rotates as it revolves. So if I'm sitting here, I can, in theory, just rotate around, right, in one spot right here, without moving anywhere. But if I were to stand up and take a walk around this laptop right here, then that would be considered to be revolution. Now, what really happens is that if I were to stand up and then as I'm walking around the laptop to come right back to where I am and I was spinning the entire time, that would be the most accurate thing of what happens. Now, everything is moving out in space. Everything is moving. So it's either orbiting something or it's in a straight line somewhere. Everything's in motion. And pretty much, as far as we can tell, every object that is doing so is also spinning or rotating as well. Now, the spin or the rotation is what causes day and night. So a full rotation of planet Earth takes roughly about 24 hours, and that's why it is the length of our day, right? So day and night, one spin, there it is. If you look over here, this is a pretty cool GIF, right? It is just showing time lapse, and you can see that over the course of the night, it's it doesn't look like this right here, like in the short term because it takes so long, but really all the stars, it looks like they are moving. Now, of course, they're not moving, right? If you could see, they're all stationary, like they're all staying in the same exact spot. It's just the Earth that's rotating that makes it look like it's moving. It's the illusion of it. And because of that, you see how everything basically stays together? Other than those like random streaks that you see in the sky, which are not stars actually, those would just be shooting stars, they're called, or meteors burning up in our atmosphere. But you see how they're all basically staying together, right? Like this one star stays next to the other star that it's next to it as they move together through space. Really, they're on their own, somewhere out far in space, and they may not be, even though two stars look like they're right next to each other, they could be an incredible distance apart. Just from our perspective, they look like they're right near each other. As they move throughout, all the stars are basically on this set path compared to us, and they look like they don't move. A long time ago, ancient astronomers would look up at the sky and they'd be like, all the stars are basically where they're supposed to be. They have this set path that they move throughout the sky. But there's a couple of these stars that just look like they wander. They don't follow the rules of all the other stars that are out there in the night sky. So what are these wanderers? Well, that word wanderer translated to planets. And that's how we discovered some of the earliest planets. Because at first they look pretty much indistinguishable from other stars until you realize that it wouldn't really make sense for them to, they're not following the same rules as the other stars are. So maybe they're not stars. And then we find out, of course, that they are actually planets. Now, this is a pretty cool little image right over here. How do you think the photographer took this picture? What they did was they basically let the light come through, and this is basically the night sky over a long period of time. So it's like a time-lapse image that they combined together here. And I know it's almost impossible to tell at this point, but every single one of these lines here is really just a dot. But over time, as it drags its way across the sky, that's what it looks like over a longer period of time. Now, I love this image right here, right? Because as compared to this one here, which shows the night sky moving, that's only because we are moving with the Earth as it spins. But what if you weren't moving with the Earth as it spins? Well, that's what you're seeing right here. Notice that as it moves, right, the night sky stays perfectly still, and that's really what's happening. I love this just so much. It just gives so much information. Now, what looks like should happen is that it looks like this tent should be sliding down to the left as it tilts that way, right? However, it doesn't. The reason is because gravity is pulling everything down, and down is always right underneath the tent. So right now this makes sense because we're on top of the earth, so is this tent. But as this starts to twist, it looks like it should fall down to the left, but that's not really what's happening because down is directly below it at all points. So you can see that it's the earth that's twisting and rotating and moving, and the sky stays exactly where it is. Here's another image that just kind of shows you exactly what I'm talking about. If this camera stays perfectly still, notice that the stars don't look like they're moving at all over the course of the night. And then as the sun comes out, it's too bright out, so you wouldn't see any of the stars. But then, of course, when we rotate away from the sun, we can see the night sky in all of its glory here. So another pretty cool image. All right, the next definition I'd like you to write down is revolution. So it's the elliptical motion of a body as it orbits another body in space. I would like for you to draw this image right here. This image is an ellipse. Ellipse is really similar to a circle. It almost is a circular orbit, but it's not quite. It's like a circle if you just, so if you draw a circle and then you just stretch it out a little bit. That is what an ellipse looks like. Now notice that the Earth has an elliptical orbit around the sun, and the moon has an elliptical orbit around the Earth. Orbit can mean two different things. I'd like you to write both of them down too. Orbit could be a verb, and it means to travel around. It just basically means the same thing as revolve. Or it could be a noun in terms of that, oh, that's its path that it took. It followed its orbit. Or it would mean the same thing as revolution in that point. So orbit and revolution are basically the same exact thing. Now notice that both of these things, as they're moving, they're also rotating, but they're rotating in one spot here. You can't see this, but the sun is actually also revolving around something. What do you think that is? Remember, all the stars in our galaxy are orbiting around the black hole that's at the center of our galaxy, and we think that that exists within all galaxies as well. Here's a classic image right here. This exasperated mother-sun trying to deal with all of its kids that are running around like crazy, but all that's really representing is how they're all in orbit around the sun, just moving around. And the one that's closer to it right there, right, Mercury, and then gradually some of them get further and further away. Here's another video I'm highly recommending for you to watch. Just another, it's either Minute Earth or Minute Physics. I think this one's Minute Physics. We start watching a lot of these Minute Physics, and then we almost never watch the rest of them again. And then we transition over to Minute Earth videos, which are a little bit easier to understand and I think a little bit better done. But these are the ones we have for now, and they're still pretty great. Okay, let's look at this diagram. A couple questions for you. Okay, as you see, is this showing revolution or rotation? Well, it actually looks like none of them are rotating. You can't really tell if they're rotating or not. It looks like they're just kind of stationary, right? So we'll say that they are revolving, right? They are revolving. Now, how long is a complete revolution for Earth? How long does it take for one of these to revolve around, for it to go around once? The answer is about 365 days. It's actually technically 365 days and 1/4. And that's why every 4 years we have what's called a leap year, where we add up those extra 6 hours and then it becomes an extra day of the year to account for that. Why does the outermost planet have the longest orbit, right? Look how much longer it takes for this to travel around. So as this one travels around, Neptune, look how many times this one over here, Mercury, is able to travel around. It travels around so many more times. So what that means is that for one full revolution of Neptune, let's say it's one Neptunian year, there are so many more years, or Mercury years that happen right in there. So a year on Mercury is not very long compared to a year on Neptune, right? So just something for you to keep in mind when we talk about what a year really means. Year is relative depending on where you are in space or where you are in the solar system. Now, the last thing it says, what is inaccurate about this model? There's probably a bunch of things you can think of, right? One thing is the scale of it. The sun should be much, much bigger, right? Another thing should be the scale, the size in between the planets. They should be much further apart. Fine. Another thing is that what is inaccurate about this model is that the shape of it, right? We just learned that all orbits should be elliptical, and these are almost perfectly circular. So they should be stretched out a little bit, but we're going to forgive it because it's still a very useful model for us to